So yeah, so the whole circuit, this can be drawn in terms of discrete diagram. Here is the program. Okay.
So sir, means whatever we are doing, whatever other connections we are doing in the classical computer, same thing currently by using this. That's the thing.
So in fact, I have not shown you. So this I have shown you only.
So that means LDPC code and all those.
Yeah, everything is there. Everything. All are there. So good thing is that now. So what I have shown to you is still bit flip. We have to still talk about phase flip. Okay, and then only everything happens. By the way, this is the POSIX implementation. You can see that implementation, quantum register, classical register, installation. Okay, and then create the quantum circuit, and then control out, for those bits, you know, all those things you can and do the measurement. Okay, the whole program. I think by now you might be knowing how to do this, right? So here is the output. And the bit is corrected to 0 and 0. Now we talk about the phase shift now. So what happens? You know that phase shift and bit flip are huge, right? So if you take phase shift and apply it to head on, you get to bit flip. Okay, and you can check by doing the matrix calculations, right? Similarly, you know, not so basically, you know, edge, you know, and you can do the sigma z. Here is okay. Here is the circuit. Here is the circuit for single bit flip. And we modify the circuit by putting these three head-on gate at the beginning and end. So suppose this is a single phase flip. So we put three head-on gate here, three head-on gate here. Rest of the structure remains same. So what it does, this whole thing is equivalent to single bit flip because of the duality, right? This H at the beginning and the end. Okay, that is the key thing. This one you see, I mean everything is there. Whole thing acts as a single cube. Okay, the phase flip converted to single cube. Single bit flip. Okay. So basically, this is the implementation for bit flip. Phase flip, and we have the code here. So I think that we can use. Now, so I have shown you how to write single bit flip and single phase flip. Same ideas actually people should actually use to arrive at this code, which you know. So 1 qubit alpha cat 0 plus beta cat 1 is protected by alpha cat 0L plus beta 1L, which is having this kind of thing. So basically he is using 9 qubits. So in order to protect single qubit, he used 9 qubits. So that was the discovery of quantum error correction. This code can correct any single bit flip and any single phase flip arbitrarily. And this is a very powerful thing. But later on, people actually did a better one, which is like 5-1. 1 qubit can be protected with 5 qubit. Of course, then just like classical coding, we have different bounds, you know. And 7-1 is also there by Steam. Steam constructed 7. Same time, all this is happening immediately same time. After pretty short discovery, within the same couple of months, we have the other discovery as well. Okay. So this is the circuit for short method. Okay. Phase flip encoding, bit flip encoding, bit flip decoding and correction, phase flip decoding and correction. So single bit error. Okay. And then this is the implementation for the show. I think this is available for you in form, right? By the way, after Peter showed discovery, a lot of things have happened. As I mentioned, Steam came in 1996. Topological codes are very, very important. I think topological quantum codes are actually the real thing. There are a lot of variations of surface codes. I think Pradeep is at IIT Madras, who is really good expert in topological codes in India. They can show code, hexagram codes. Finally, now we have a little bit vacuum code. Right, so all these things are happening. Actually, unfortunately, still there is no good book. There is one book. I thought of writing it long time ago, but still didn't get time. But anyway, that is something that still someone can look at it and then make a nice. A lot of it actually is there. Okay, and so this is the comparison, you know, for different qubits, complexity, decoding algorithm, what are advantages, disadvantages. So I think I will share the slides and you will get it. And there is CSS construction which is popular. I will talk about it maybe in the next course. So basically taking two binary codes and their combination can give rise to quantum algorithm code. Okay. In fact, so after that is orthogonal geometry was done independently by Keter, Shore and Shore. I am going to talk about in the next session how you can construct from GF4. Something very interesting connected to stabilizer. So essentially now what people do, there is a group theoretic framework for correcting quantum understanding the whole thing. So polyerrors actually can be understood in terms of groups. Okay, it forms a group mathematically, and then you can study it. I'll talk about it, the basic in the next session. A fact theory was given in 1997 by Neil and Lefner. Necessary is building potential for quantum error correction. And of course, this whatever has been done on bitfit can be done on qubit. Whatever can be done on qubit can be done on qubit. This G right? And all these codes. Actually, by the way, there are what I told you about the symmetric means bit flip and phase flip same amount, but actually in reality phase flip happens more than bit flip. So then the whole theory has been developed for asymmetric model of quantum computing, right? Asymmetric quantum codes have been developed. And everything is there, hanging, hexa, polar, chipson, this is very incomplete thing. A lot of things are there. And now you see this is the crystal's result. The space-time is nothing but a quantum error correction. The black hole, the correction with black hole, quantum error correction, and the space-time. It's a nice one. There is a thesis also available on this matter actually. John Pascal calculated who has done a lot of work in this area. Okay. And very recently, this is you see 21st November this year, Penrose tiling. Again, also Penrose comes in the picture. This quantum electric code. Tiling is a very beautiful business mathematically, and that we think also as a quantum electric code. Okay, especially surface code. Cryptographic tilings are there, and I think this is a very recent news. I think 2nd of December. There is an Australian company, Q Control, which has come up with a nice software for actually topological quantum electric that boosts performance by 1,000 times. Really nice discovery. So there are a lot of way things have been modified for different kind of architectures. Things have been proposed. In this lecture, I gave you the basic idea of actual early discovery, and I think if you look at the entire thing, probably you will look at 50 lectures on all types of things. So I think there is a monograph which I wrote long time ago. It's available online. The geometry related for the code. It's connection with finite geometry. I will talk about the finite geometry problem in the next session. These are some of my collaborators. Our Gilbert, Mr. Victoria, and David Green. Now at Stable. Anyway, thanks to all my audiences which have supported our work. If you have any questions, I will be happy to answer. Thank you. I think I'm not taking enough time.
What's a cube date?
Means there is binary, I talked about zero, right? So when you say the binary, d-dimension, right? So now two will some over d. From qubit to qubit. Okay. A lot of construction is there. Thousands of papers are there now, right? So somebody has to really write a nice and not so why people are not writing. Still this is missing.
Because it's so extensive.
Pretty massive. Probably one has to form a huge team to actually do the work. Yeah. Pradeep is a very good expert in India at IIT Madras. He is, in fact, the initial group theoretic framework was given by his group when he was in US. So he has done his group, group in IIT Madras. So I think after this was in different directions, field has gone actually. Right? In fact, especially topological codes are very, very useful for the real.
So the phase that you said is so common. Is it because of the cube not staying in state for a long time? Is that what
Yeah.
phase that have been more common?
So this was an early history basically, right? Early history, I think it's a starting point. In the next session, I am going to give you some, the mathematical framework, early framework. Actually, I have only kept in that area only the binary one. Later on, now one can actually describe everything in terms of finite rings, especially commutative rings can be used. Mathematicians, they like the structure, and then they develop the whole theory. But don't worry about any applications, right? That material is there. Okay, so but I will talk about the early mathematical framework so that you know you understand what is that.
One question. What we have learned in last few lectures, last days, when we perform measurement, so quantum property is lost, it comes into classical domain.
Right.
And here we are applying error correction. So So are we applying the error correction in classical domain or the quantum domain? I'm still confused because once I do the measurement, it comes into classical domain, and whatever theory we are applying, the theory which is available in classical domain,
Actually,
same theory we are
in
applying.
terms of implementation of these ideas, basically what is happening, what kind of hardware you are looking at. Because see, fault tolerance can be provided at the hardware level, also at the software level.
Yes.
Once the output is there, then you can do the corrections. Now depends how do you implement and implement which scheme. So like superconducting qubits are a different architecture, and there are some other kind of architectures are there. So now I would say that there are different companies and groups which are doing different level. So at both level I am saying that they do it like software level, a lot of things are done, and at the hardware level also, depending on how you realize something. Okay, so actually in terms of error correction, I would say that
So we have to apply the measurement.
Yeah.
We will be able to do some correction.
yeah.
So measurement is required, and whatever we have learned till now, everyone said that once we do the measurement, quantum properties are lost. Now we are having only classical bits. So whatever classical bits are there, whatever theory is available.
So basically when we do
classical-
measurement, here, for example in the syndrome as you saw, now we are getting 0, 0, 0, 1, 1. So based on that I can actually decide what.
So that's what I'm saying. Now why we require quantum codes? It's simple. I have received some bits, right? And I have measured it. So I know it is 001. Right? 001. So whatever theory for classical computers are available for error correction, it will be applied directly. Because without measurement, we cannot do it.
Yeah, so this syndrome calculation is also only after measurement only, right? You are getting 0, 0, 1, 1, right?
Then why we are applying Hadamard gate and all other things? Because we are doing both.
So that's the whole architecture. So basically when we are executing some algorithm, the architecture is there, right? So syndrome is a measurement that we are doing. Only we are measuring the last 2 bits, right?
You are reducing the probability of getting an error by using quantum code. So that's what the difference is. Correct? Is that correct, sir? By using quantum codes, what you are doing is reducing probability of
What you are
getting
correct,
an
you are
error.
using it.
Correct? Yes. That's what the quantum code. Any further questions?
Thank you very much, sir, for enlightening us with the basics of error predictions, encoding and decoding. And you have given very detailed insights how qubits are getting changed, what all the errors, if at all, are there. Like even a single qubit, if there is an error, how you can correct it, right? So with this, I would like to summarize the session. Like sir has explained or started with the very basic principles of error corrections. Later to the key properties and how those key properties are related with the error correction methods. Also encoding and decoding techniques are very well covered, whether it is starting from a single qubit or two qubit with code. Afterwards, sir has also given various different companies which all are working on this error correction methods. So I hope you all are very much enlightened with this session. And I think we are looking forward to your coding section as well in the afternoon session. So thank you very much, sir. Once again, I would request all the participants to give the beat of the So participants, afterwards, after this session, we are going to have the quiz and the paper session answer. It will be given by Malvin, it will be in the book, and then you can proceed with that. Afterwards, we are having lunch, and after that, and then a small value.
So, right? Yes. Just
You can make a paper cut.
Connect framework, so basically what connect which is very important and useful here is sometimes it is not covered. So basically I am going to give you some slowly build the effective foundation for you so that you can really understand the basics of quantum mechanics and effective framework. Okay, what is happening? The talk is very elementary. I am not going to use any deep mathematics. Towards that, of course, I will show you two results which are important. But there I probably will skip the proofs at the beginning, but at least you know what are the master results. Okay. So I hope that is the target, right? So I will cover everything. All mathematics I will cover, but that we require to understand the mathematical framework of Gaussian vectors. Okay. So that's why I call it coding for quantum computing. So I am going to cover some finite fields, vector spaces, linear codes in detail. Then basics of quantum errors. There are two kinds of errors as I mentioned. And then the combination like bit with phase field and the combination. And normally, phase field happens more. So there is a symmetric quantum code. I'm not going to cover any of the symmetric quantum mechanical code, but basically the classical setup of the error group E that was there. And key thing is that we will see that this error correction business corresponds to a finite geometry problem. So geometry we know from our school days or high school. So geometry over fields is one thing, geometry over finite field is another thing. It's finite geometry, which is very beautiful. Okay, so I will talk about it, and then that problem converts into GF4, which is a field with 4 number of elements. So, and then that gives rise to additive code business. And finally, I will show you what was the results that are obtained in that 1998 paper. So I will give you the basic idea of the things. Okay. Okay. So fields. Basically, field means what? Cricket field, football field. Right? Football we play football. Cricket field. In the cricket field, playground we play cricket. Right? Similarly, in mathematics, field means a set of number system where we can play with all the 4 operations: addition, subtraction, multiplication, division. Very simple. You don't need to memorize all those rules. It's very simple. If you can do in a system all the 4 operations: addition, subtraction, multiplication, division, you can actually play in that field, right? So here we call it as a field. So well-known example is real line. All real numbers, they form a field. Okay. Before that, a set of rational numbers. That is also a field. Right? You can add, subtract, multiply, divide, all rational numbers. Similarly, real line is a field. Another extension is complex numbers, complex field. So you can add 2 complex numbers, multiply, all those 4 operations you can use the complex numbers. These 3 fields, real, so rational, real, and complex are building block of most of the mathematics that you see. But this, in terms of computers, we require what is known as finite field. So field where I can do all the 4 operations with numbers, but basically number of elements in the set is finite, only finite many. It could be, so what is, if I ask you a question, how many minimum elements you require for a set to form a field? Any answer? 2. Because you require additive identity and multiplicative identity. 0 and 1 is a very basic thing. The smallest field in the world having 2 elements, 0 and 1, and that's why all your computer is based on binary. And you can play with bits. Okay, that's very basic thing. Okay, so I will start. So there is a field with 2 number of elements. So I am going to cover about this ring and field, and it's basically, if you look at integer modulo n, so what you do, you take all the integers, divide by n, possible remainder 0, 1, 2, 3 up to m minus 1, right? And we know that for certain values of m, integer modulo m is a field. For example, m is equal to 2, it is a field. I will show you examples. 3, it is a field. 4, it is not a field. 5, it is a field. 6, it is not a field. So actually, essentially for any prime number, integer modulo p is a field. But I think this you might be knowing. So then I will show you some constructions how we construct field 4 number of elements actually. And then actually I am going to show you how you can construct quantum algorithm code in field 4 number of elements. So that is a really basic thing. Okay. So this is our set. It is a modulo n, having elements 0, 1, 2, 3 up to m minus 1, and 2 operations are addition. You add the numbers and you divide it by n, look at the positive remainder. Similarly, if you multiply 2 numbers, right, divide it by n, look at positive remainder. For example, m is equal to 2, we have only 2 elements, 0, 1, operation is plus 2, multiply it by dot 2. So you see that we can make these tables. Actually, these tables are easy to understand, the field. For example, with respect to addition, this is the addition table. If you see here, so there are 2 elements. So basically, 1 is, so basically every element has the inverse. So every non, so 1 has inverse what? 1 plus 1 is 0. So we got 1 minus 1, so 1 is equal to minus 1, which is same thing as plus 1, right? So 1 plus 1 is 0. This is something you can observe. Normally what we check, so every non-zero element in the multiplication should have an inverse. So if you see there is only one element which is 1 and it has inverse, so 1 into 1 is equal to 1, right? So 1 is self-inverted, okay, that is there. Now similarly in case of m is equal to 3, we have these two tables, I can prepare easily. Now you see that here, so everything is very well defined. Now in terms of multiplication, I should check the inverses. So 1 into 1 is 1, so 1 is self-inverted. 2 into 2 is 1, modulo 3, right? So that means inverse of 2 is 2. That means 1 by 2 is equal to 2. 1 by 2 is not equal to 0.5, right? This is a different system altogether. And that is the normal day-to-day routine. You know that okay, 1 by 2 is 0.5. No, here 1 by 2 means 2. Okay? But how? 2 into 2 is what? 4. Modulo 3 is what? 1. So 2 into 2 is equal to 1. So 2 is equal to 1 by 2. So 2 is equal to 2 inverse. So if you have daily, we don't handle these things. Somebody applies counterintuitive, right? But this system is really important. But because 2 into 2 is equal to 1, so 1 by 2 is equal to 2 inverse is equal to 2, right? So 1 by 2 is equal to 2. It's not 0.5 here in this system. Okay? So this was for m is equal to 2 and m is equal to 3. Then we can go to m is equal to 4. Now there is an issue. You see that addition table everything is fine, right? But with respect to multiplication, so 1 into 1 is 1, fine. 2 into 2 is 0. So we don't have any inverse of 2. 3 into 3 is 1. So inverse of 3 is 1. 3 is equal to 1 by 3. 2 is equal to 1 by 2, right? But 2 has no inverse. And this creates a problem. So this is a 0 divisor. This is known as 0 divisor. Okay? Basically, field has a very important property, I think. In the real complex, you know every day you use this law that if A into B is equal to 0, then either A is 0 or B is 0. But in ring, neither A is 0 nor B is 0, but their product is 0. That is a possibility. And here it is the case. 2 into 2 is equal to 0. Not 4. Right? Both 2 and 2 are non-zero, but their multiplication is 0. This creates a problem. So I would say that I love this because I have done that page. This is on this ring actually. The whole linear algebra structure changes. Actually, if you look at a matrix, you might have heard about row rank and column rank. For Z4, row rank and column rank is different. Normally, row rank and column rank is same. Okay, for a field. In beautiful, interesting mathematics comes actually there, you know. So that is the case. Okay. So it is not a field. So question is, how do you construct? So basically, 2 I know there is a field, 3 I know there is a field, 4 I am not able to construct using this method. So I need to develop some new mechanism. 5 I know it is a field. 6 again is not a field. Basically for any prime we know how to construct a field. So let us see how do we construct a field with 4 number elements. And our quantum error correcting course will be based on that field only. Okay? So now you see, you look at the analogy. Who invented complex numbers and how and why? You see, on real lines, it's all mathematics is all business driven, right? You are solving some business problem, and it leads to some equation. Now the equation is there, you should know how to solve it. Now here, in case of reals, you know, any degree 2 equations you can look at, right? You can solve. So if you look at x square plus 1, there is no root in the reals. There is no real number. If you square it and add 1, it will get 0. Right? So that means we need to extend the domain. Our real line is no more sufficient. Right? So what we do, I say suppose I is the root of this equation, which is not on the reals. So that means I square plus 1 is equal to 0. That means I is equal to square root of minus 1, that you all know very well, right? And I attach I to it in this term that A plus I be such that A and B are reals. I found this set, and then this set becomes field. All four operations are satisfied. Beautiful, right? And what is I is the root of this equation, that I squared plus 1 is equal to 0. So what is this equation? X squared plus 1 has no root in the ground field, and I extended it by taking a root which is higher than the ground field. Okay, I get it. So I hope this is very clear, right? The same technique I am going to use for constructing field with 4 number of elements. So what I have over Z2, I have only 2 elements, 0 or 1, right? So if I look at degree 2 equations, because here, in order to do this, I did it with degree 2 equations. So a general degree 2 equation is what? A square plus B plus C equal to 0, where A is not equal to 0 and A, B, C are in Z2. So how many equations there possibly there? If A is not equal to 0, so A is 1. So equation is x square plus B plus C is equal to 0. Or B has 2 choices, C has 2 choices. So total total equation will be 4. Right. And now I can check which one is irreducible. So because this equation is irreducible, which has no root in the ground field, we call it irreducible. You cannot factor in the ground field. You can factor say x plus I, x plus I, but you have to go outside. Right. In the similar manner, so if you check x square is 0, it's not going to work because this is reducible. 0 is the root in the ground field. X square plus 1 is equal to 0 is also not going to work because x to 1 is the root. 1 square is 1, 1 plus 1 is 0. This is not going to work. X square plus x equal to 0 is the root. This is also not going to work. What is left is x square plus x plus 1 equal to 0. Now, if I substitute x equal to 1, what will happen? No solution. 0, no solution. Although this is a loose method, but it's enough here. So 0 and 1 is not a solution in this field, right? There are only 2 possibilities. I checked all of them. It is not there. So this equation has no root in the ground field. In the binding Z2, which is 0, 1, this equation has no root. So we have found an equation which is irreducible over the ground field. Right? Now I can use this equation to build field with 4 number of elements. So what I do, I will say suppose alpha is the root here. There I symbol was I. Here I will call it I will call it alpha. Suppose alpha is the root here. That means alpha square plus alpha plus 1 is equal to 0. Right? And then I can build field with 4 number of elements. This is after the name of Vivaris Galois field GF4. A plus alpha B such that A and B are in Z2. And alpha is root of this equation. Alpha square plus alpha plus 1 is equal to 0. Now, surprisingly, this GF4 field satisfies all the properties of addition, subtraction, multiplication, division. So we have found a field with 4 number of elements. Beautiful thing, right? You see, here is the table. So I can just, now, when you do some calculations, you will see that so 0 plus 0 is 0, 0 plus 1 is 1, 0 plus alpha is everything is same, when you add 0. 1 plus 0 is 1, 1 plus 1 is what? 0, because the ground field is 0. Everything is, whenever we are adding two things, coefficient should be reduced with the ground field. Okay? So 1 plus 1 is 0. 1 plus alpha is alpha square. Why? Because alpha square plus alpha plus 1 is equal to 0. 1 plus alpha is equal to minus alpha square. Minus 1 is same thing as plus 1 modulo 2. So 1 plus alpha is equal to alpha square. Right? So 1 plus alpha is equal to alpha square. So basically 1 plus alpha is equal to alpha square. Similarly 1 plus alpha is equal to alpha. And you can fill the table nicely. With respect to addition, everything is satisfied. Now we want to check whether with respect to multiplication every non-zero element has inverse. So I can check yes. When I form a table, you can see that 1 into 1 is 1, so 1 is self-inverted. Alpha square and alpha are inverses of each other because alpha cube is 1. You can actually calculate that, right? Alpha cube will be what? Alpha cube is equal to alpha square times alpha. Alpha square is 1 plus alpha, so 1 plus alpha is equal to alpha is equal to alpha square plus alpha. Alpha plus square plus alpha is equal to 1. Don't you think it's a beautiful thing? So alpha cube is equal to 1. Now, a common confusion that arises that it looks like a cube root of unity. Omega, आपने सुना होगा कैसे? Omega cube is equal to 1 and omega square plus omega plus 1 is equal to 0. लेकिन उस omega और इस alpha का कोई रिलेशन नहीं है. वो डिफरेंट डोमेन है, वो इनफाइनाइट डोमेन है, ये फाइनाइट डोमेन है, राइट? वहाँ पे क्या है? कॉम्प्लेक्स नंबर है, यहाँ कोई कॉम्प्लेक्स नंबर नहीं है, राइट? This is a different story altogether. In fact, एक्चुअली यहाँ पे अल्फा स्क्वायर को अल्फा का कॉन्जुगेट बोला जाता है, बिकॉज बिहेवियर बिल्कुल सेम ही है, लेकिन ये वो नहीं है। वहाँ पे क्या है, ओमेगा की वैल्यू स्क्वायर रूट में आप निकाल सकते हो, यहाँ वो सिस्टम ही नहीं है, राइट? यहाँ पे वो सिस्टम ही नहीं है, राइट? गॉट इट? दिस इज समथिंग ब्यूटीफुल, राइट? सो वी हैव गॉट फील्ड विद 4 नंबर ऑफ एलिमेंट्स. Any question at this point? Because यही फील्ड से क्वांटम को कंसीडर करेंगे, so I hope you understand this really well. This is our playground for field with 4 number of elements, right? Now there are 3 ways we can represent this. One is bit representation, because what happens, a plus alpha we have written, a and b are 2 choices, so could be 0 0 0 1 1 0 1 1, so I can write down everything like bit. So this is known as bit representation of the field. Then there is a polynomial representation, 0 alpha 1 1 plus alpha, like that you can also write. And also you can write in terms of powers. You can see that I have written the power 0 alpha 1 alpha square, right? These 3 representations are used. So normally we deal with this. So basically alpha means what? So from here what is alpha, can you tell me? So 1 plus alpha is this, right? Which is 1 1, right? So 1 plus alpha square is 1 1. So actually when writing programs you can just make a table, do this addition and multiplication table and do the calculation based on those things, right? Essentially you must have heard about bytes. Byte, kilobyte, megabyte, right? Byte means what? 8 bits. And those 8 bits are coming from field with 256 number of elements. Okay? So that is also a field, just like this field with 4 number of elements. उसका polynomial अलग है to construct that. You know, that's why we do look at SC character and so on, but that is the backbone. That is the power of mathematics that we can do, right? I hope you understood up to this point, right? The power of alpha, polynomial representation, bit representation. Similarly, you can do with 8, so you can do 3 polynomials. Okay, and then you will find 2 polynomials, x cube plus x square plus 1 is equal to 0, x cube plus x plus 1 is equal to 0, which are irreducible, having no roots. Okay, and you can take, now the question is which one I should take. जिसका जो मान है वो ले ले. Somebody can take this, somebody can take that. You will get the same field. I mean, they are kind of isomorphic. In one way, you can just rename kind of thing. Okay, so they are straightforward. You can pick up any polynomial. And here is the, you see all the calculations. Here alpha is equal 7 is equal to 1. Okay, so actually you see that the non-zero elements forms a group here also, very group in terms of mathematical terms. Okay, all the calculations you can do. So this is the field with n number of elements, 0 1 alpha alpha square up to alpha is equal to 6. Okay, this is the power representation. Similarly, there is could be polynomial representation or bit representation, right? So this way you can continue from Z2 with 4 number of elements, 8 number of elements, 16 number of elements, 32 number of elements, up to some 2 raised to n. This kind of construction with a polynomial of degree m minus 1, and then we have take fx with degree m polynomial which is reducible, and you can build the entire system with power of alpha. Right? So you can go up to any domain. In fact, I will show you a field with 16 number of elements. With this polynomial, x is for 4 plus x plus 1 is equal to 0. Right? So now you see that polynomial representation, power of alpha is for 0, alpha 1, alpha square, up to alpha 14, and the bit representation. Got it? So I think you understood fairly well about the basics of finite field. You can also start with field with p number of elements, because Zp is a field, and you can build up to field with p is for m number of elements, which is having q. So basically, a set having q elements will be a field if and only if q is a prime power. Right? 6 number की field नहीं मिलेगी हमको. It has to be a prime power. Okay? This is a very very important. Now vector space हम लोग पढ़ते आ रहे हैं, but यहाँ पे actually so it's very interesting when we change the field. So now this fq is a field with q number of elements. Fq is all n tuples. Now vector space is what is vector space? Vector space is a playground for vectors. Simple. Take 2 vectors, add them, you are again in the set. Take a vector, scale it, you are again in the set, right? These are the basic characteristics I am telling you, and you can list all those groups which they follow, right? That's a very basic thing. Now each vector space has a basis. So basically, for example, if you take q is equal to 2, okay? So even this works out even in the higher case also, with q number of elements. So this vector space has a basis. Basis is a set of elements which can generate whole space. and they are linearly independent. These vectors are linearly independent. Means if you take linear combination of them, put it equal to 0, all scalars will be 0. Right? So you cannot find a combination of them which is equal to 0, right? That is a basic. So this set B is equal to U into V is a basis having n elements, and this is known as dimension of V and Q. Okay? So basically this is a P. Now you see, this is a binary vector space. Vector space which is built on binary field having only two elements. Geometry अब बिल्कुल अलग हो जाएगी. Right? So in RQ, how many lines are there passing through origin? R is a real number, right? How many lines are there passing through origin, which are known as one-dimensional space, right? Infinitely many. You can draw in any direction, right? पर यहाँ पे आप count कर सकते हो finite field के case में. How many will be there? There is a nice formula, okay, given by Gauss. Okay, you can actually count how many lines are there. So actually, vector spaces over finite fields you can touch, feel, smell. So the real complex one infinite business, right? You cannot do that. But here you can actually feel everything. You can actually take subspaces out and so on and build as well. Okay? And also there is a subspace. Subspace of this V and Q is, you know, if you take any two vectors, take a scalar, then linear combination again is the set, right? And for example, if you take V32, so V32 means what? Over binary, there will be 8 elements, right? Over vector space. I can take 1, 0, 0. So basically, if I ask you a question, Z2 raised to power 3. Z2 raised to power 3 is a binary vector space of dimension 3 having 3 basis vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, right? And the combination will give you 8 elements, right? The question is, how many one-dimensional subspaces are there? Means how many lines passing through origin of this vector space? Yes. No, 7. 7. You take any non-zero element, you know, out of the 8, except 0. 0 will not do that thing. Any non-zero element, there are 7 subspaces, so 7 lines passing through origin, right? Bit different. Now you can feel everything, right? This is something very useful. This is, you know, so this is a one dimension. Similarly, two dimension, I take these two vectors, they linear combination with lambda 1, lambda 2, which are in 0, 0, 1. You get 4 vectors. This is a subspace of dimension 2. So this is the basic linear algebra that we need to understand. Okay? Now basics of linear code. We saw this code 0, 0, 1, 1, 1. This is the one dimensional subspace of Z2 raised to power 3. 3-dimensional vector space, right? So now we know this is a linear code. Linear code means all the basis elements can be put as a generator matrix and you can generate the vectors out of it, right? So essentially, this I think is realistic. We have already talked about it. So normally, code means, so FQL is a vector space of dimension n. A code is simply a subset with parameters n, m, d. N is the length of each vector. Capital N is total number of code blocks, and d is the minimum Hamming distance. I think Hamming distance you know the number of places they differ, and minimum Hamming distance which is the minimum of all, right? For all pairwise. And linear code means a subspace. A k-dimensional subspace, notation is NKDQ. K is a dimension, right? And you know that if the distance is d, we can collect d minus 1 by 2 error. So that is the. We can also define inner product on the vector as a standard inner product. Okay? And actually, weight of a vector is defined as distance between x and 0. Okay? This is the normal notation which are known to you. We can, once we have the inner product, we can define the dual space, C equal to all the vectors such that the inner product is 0. So basically, take the subspace C, look at all whole space and check, so one by one check which vectors are orthogonal to C. You will get another set which is C part, right? Okay, so that is a null space. Now, the interesting thing, actually over real complex you know, intersection of C and C part is similar to 0. There will be 0 vector common. But over finite field, that is not the case. Okay, there could be more things there. Okay, so that's really interesting. Anyway, so C is actually self-orthogonal, C is subset of C part, self-field, C equal to C part. That's the basic notion of coding. And so this linear space is given by a generator matrix, standard matrix, when you put all the basis vectors into matrix form, you can diagonalize the initial thing which will be identity, right? And then some matrix A. This is the basis for generating C. And also there is a Tate matrix H which is orthogonal to G and which is described by, if G is that, H is minus A transpose I and minus A, okay? And so sometimes we use describe code with respect to Tate matrix, sometimes we describe code with respect to Plato matrix. Okay, both are equivalent. So I think probably this is not needed, actually we can skip this. Now we come to the quantum errors, okay? So in terms of quantum errors, you know, I'm just recalling this again. So it says Hilbert distance. What is Hilbert distance? So vector space which is complete with respect to the infinite reduced distance, right? So that is Hilbert distance. So as you know, the qubit lies in the Hilbert distance, mathematically, right? So the resistor you see is actually building from, so methodically you can think of it as a Hilbert distance. Okay? And these are the basic states, and the general state is something like this, right? The Ci is a complex number, normally is complex number sum, okay? And polynomials are there, I think I just mentioned to you, bit flip, phase flip, right? You already know from the earlier lecture. These are the basic errors. So as I mentioned, the quantum error models, there are two kinds of codes, symmetric and asymmetric. In asymmetric case, phase flips happen more as compared to bit flip. This is when we observe. Okay, and the phase flip is almost unequal and it's symmetric. Okay. Now we can build the error group. You see what we do? We have our get Vn2, which is Vn, Z2n, or binary vector space, having 2 raised for n elements, right? And basis, so basically now we take them or each vector V in Z2n and form this ket V. This becomes a basis. Actually, it's an orthonormal basis, right? But I'm not worried about it. C2 raised for n is a Hilbert space. 2 raised for n dimensional Hilbert space, where our quantum resistor is sitting. Okay? And errors are nothing but unitary matrices acting on here, right? So quantum errors acting on Vn. So unitary linear operator on Vn, right? So what kind of errors are there? I raised for lambda, x of a, z of b. X of a and z of b are two functions. I will tell you what are those functions. For any vectors a and b in Z2 raised for n. Okay, so actually this whole set forms an error group. It's a non-abelian group. Things will not come out. A typical element here is E, I will call it I raised for lambda, x a bar, z0. What are x? X a is basically bit flip kind of thing. Each component wise. If b is a vector, binary vector, and a is also vector. Sum means bit flip, right? If it is 0, then this will be, these two will do the bit flip. And that means phase flip, right? Minus 1 is for a, minus 1 is for b dot a, ket v, right? This is the, so when we have this basis state, we apply x of a, we get this, and z of b, we get this. These are the two basic operations. Essentially, all the elements in the error group are like this, okay? This we are actually fully bringing error group from those poly errors. A typical error operator will look like this. Okay, this is the formula for that. Now once we have this, now I can build some properties of it. Actually now I will formulate a finite geometry problem. So you see, so that the element xa and zb indicates that there are bit errors in the qubits for which aj is equal to 1. Okay? And phase errors in the qubits for which bj is equal to 1. अगर ai में कहीं पे 1 है तो bit flip है, bi में कहीं पे 1 है तो phase flip है, right? And now if we take e prime to be some other, for some a prime and b prime, some other vector, right? Then we can observe, it's very easy to see that e prime is equal to plus minus e prime e, where plus minus is nothing but depending on whether how do you evaluate this, minus 1 is for a dot b prime plus a prime b, okay? So this is actually a nice property you can observe in this group. You just compute that. So actually this induces symplectic inner product. Okay? Symplectic inner product, because if you take y equals symplectic, you take AB vector and take the product with AB, same. Actually you get it 0. So it's why that's why you know symplectic inner product, right? So basically Now, so we can get for any two elements, first component A vector, second component B vector, and other component A prime and B prime, so you can compute like this, because this is what it is. Okay, simplicity in the product. Okay, and hence this is very, very important. So basically, we have something in the finite geometry case, a finite geometry problem actually. So what is finite geometry problem? E bar is a two-dimensional vector space consisting of first component A1 into A, B1 into Bn, right? These two vectors belongs to E bar. I take a two-dimensional binary vector space where vectors we can partition, right? Like component A and B, okay? And it's like this, AI is BI, and weight we can define as the number of coordinates I such that at least one of the AI and BI is 1, okay? And similarly we can define the distance between two is weight of their difference, okay? So now we have this two-dimensional vector space, we got this result. What it says that, I'm not giving the proof, but of course I need to do some more group theory concept to arrive at this proof, but suppose S bar is a n minus k dimensional linear surface space of E bar, n minus k dimensional of E bar. E bar is a two-dimensional binary vector space, okay, which is contained in this dual S bar prime with respect to symplectic inner product. I am looking at dual space with respect to symplectic inner product, and it is such that there are no vectors of weight less than B in S orthogonal minus S, okay. Then there is a quantum correcting code mapping k qubits to n qubits, which can correct B minus 1 by 2 errors. This is the main finite geometry problem which captures the quantum correcting property. Of course, it requires a proof which I am not giving here, but if you want, you can look at the paper later on. You will understand. I have built all the basics for you. Okay? And this gives the corresponding code is denoted by NKD. So there it was single NKD, now here we write two brackets NKD. And these codes are known as additive polymer codes. Okay? Now, this can be further refined to what is known as this result. Okay? Suppose S bar is a n minus k dimensional linear surface space of E bar, which is contained in this dual S bar with respect to symplectic inner product, and it says that there are no vectors of weight less than D in S bar slash S bar S. Then by taking an eigenspace, you know, from that should be from the characters of this group. For any single linear character of S bar, we obtain a quantum correcting code mapping k qubits to n qubits. Qubit is correct B minus 1 by 2 errors. Okay, so that is a little bit more details about the theorem. In fact, now I will show you how we connect for this finite geometry problem to field with 4 number of elements. Okay, so now this is the field with 4 number of elements. I have taken here omega. Of course, initially I am introduced with alpha, but don't think this is the same omega, right? Notation is omega because that is how they in the literature. 0 1 omega square. Omega square is called omega bar, means conjugate. But this is not complex, by the way. Conjugation h bar means x square, x is 0 4, and we define a map or trace map from field with 4 number of elements to Z2, which is x plus x bar. So if you take 0, trace of 0 is 0, right? Trace of 1 is what? 0. 1 plus 1 is 0, right? So basically, this is what is a way we define trace, right? And then we define Hamming weight of U is number of non-zero components of U, right? That's the Hamming weight. Now when this is in picture, now if you take that one E bar, this vector having two components A vector and B vector, and apply this map phi of E bar as omega A bar plus omega bar B bar. A bar and B bar are vectors, omega and omega bar are elements of the field with 4 number of elements. This map, this will give you a vector of length n over field with 4 number of elements, right? And weight of U will become Hamming weight of this phi of U. Distance between U and B is distance between phi of B and phi of B prime. Okay? For B means equal to AB and B prime is equal to A prime B prime. Okay? Once we have this machinery, then beautifully, symplectic inner product of V and B can be defined like this. You see, this quantity converts into trace of phi of B dot phi of B bar. So now, why this? So if you look at this, so what is this phi of B, omega A bar plus omega bar B? and phi b prime into a prime b prime. I can simplify this. Take a trace of 1, trace of omega bar, trace of omega, and trace of 1. Just simplify this, we get the same inner product, which were defined on 2n-dimensional binary vector space. So from GF4 there is a connection now, right? In order to construct a quantum electric code from field with 4 number of elements, all I have to do is basically just look at this map and actually we look at, so basically now the theorem that I showed you, the main result is converted into something like this. So basically, given a S which is n minus k dimensional subspace of E bar which is 2n-dimensional, actually by mapping we get a subset of this which is closed with respect to addition. So that's why we get what we call as additive codes. We call it additive codes. Closed with respect to addition. And the parameters are n and 2 raised to k. The number of vectors are 2 raised to k. C is closed under protect by omega. If it is closed, then we call it linear code. Okay? So now, another interesting thing, between two vectors like this, I can define what is known as trace inner product. Because you see, motivated by this fact, right, that trace, simplicity inner product between u and v becomes trace. So I should study the trace inner product over the vectors. So we have, so u star v is trace of v, uv, right? And so which is nothing but this kind of thing where this is bar actually. Okay, the conjugate in terms of finite field. And if C is n to raised by n minus k code, the space u is this with respect to space in the product. And keeping this in mind, again we have the self-orthogonal self-dual code. And in fact, we can also define Hermitian inner product. It turns out that both are equal here. It's something like this. X and y are f2n. Hermitian inner product is xi, yi is for l, where q is l square. That condition is there, right? So now, any linear code which is self-orthogonal with respect to trace in a product, if and only if it is self-orthogonal with respect to Hermitian inner product. This equivalence is there, which is nice thing to know, so it's easy to construct the results. Okay? So any n to raised to k code is equivalent to 1, so it can generate by this kind of matrix, by taking linear combination. We get additive code. Okay? AG is some matrix, BJ is binary matrix, and K is 2k0 plus k1, number of rows. Okay? So then this is the main result now. Suppose C is a relative self-orthogonal subcode of Z with respect to 4, self-orthogonal with respect to trace inner product, containing to respect to n minus k vectors such that there are no vectors of weight less than b in C per minus C, then any eigenspace of phi over C is a relative quantum electric code with parameters n k b. That same finite geometric problem now is converted into field with 4 number of elements. So if I want to construct a quantum electric code, I just look at the field with 4 number of elements and try to construct an additive code. Okay, of course, which code will be better? There are bounds which I am not covering in this lecture, but you can judge which one is better and so on by doing those things. In fact, this is an example, general matrix. You can see that for 25 to for 24 code, there is only one row added in the Turing space. When you look at the whole code, this gives us 2159 quantum codes. So 1 qubit protected by 25 qubits. Okay, and the error correction probability is 9 minus 1 by 2. Okay, so you want more and more error correction capabilities as well. In fact, here is a table which appeared in that paper in 1987. You see, now something interesting for you to look at. These are some gaps. For given n, given length, what is the maximum distance possible? Now you see that here, say for example, if I go 14, right? You see, this distance is either 4 or 5. If you are able to construct a code which can, which has distance 5, this will be matched. That will be 5. The optimal code we will be getting. Wherever there is actual value, it is an optimal. If there is a gap, there is a gap, and there is a research opportunity for you to construct a code of that parameter. Actually, this is the old table, 1998. There is a new table now. It's still those gaps are there. So very interesting thing for you to fix these gaps. Can you construct a quantum electric code with these, these gaps? If you go with higher length, more larger gap is there, right? So you can actually, lot of interesting problems to construct quantum electric code. Okay. So that's thing. So basically, as I mentioned, there was a purely binary orthogonal geometry paper, which is having similar idea. I talk about this paper, 8404. The pentagram range is shown. If you want, you can read more about this in this paper. System level course is a PhD thesis development who actually developed a arithmetic framework. Actually, they are all same and connected. The effect will be given by Neil and Lehman and high dimension code I mentioned. I think this I showed in the morning also. And these are the different classes of codes. I think you can read the monograph where we will be more interested in the geometry. We have done those things. This was in year 2001 or so, right? Finally, this appeared in 2006. I mean, it is on archive available. And this is the book. I think probably only book on this subject, but at least you can read it. Talks about certificate and all that. It's very recent one actually. Okay, from Springer. But I think still there is a lot of scope writing a good book in this area. I think that's all. I think if you have any questions, I think I have not been too mathematical, but I gave you some feeling. And probably you can go and read more about that paper, right? So I left it for GF4. You can go to higher, and people now talk about purely ring-based, commutative ring-based, because it's error group they can analyze from a arithmetic framework, right? So all those things are possible, right? If you have any questions, I will be happy to answer. मैंने ज़्यादा किया भी नहीं, थोड़ा सा. But that's a beautiful thing, right? So if you master this technique, right, actually you will be able to understand more. Otherwise, this jargon mathematics that is coming out will always be problem. So essentially, you require strong linear algebra over finite fields, and also finite fields to some extent, and also proof theory. Okay.
The last table that you showed us in the description,
Which one?
right? The last table showed the description, right? More, people with M, K, and this.
Yes.
So does that mean that if you're able to construct quantum codes with higher distances?
So right now, suppose we look at 5, 6, right? So this means for 17 length and dimension 3, we have a code constructed of distance 5. Upper bound is 6. So this gap is there. We don't know it. So if you are able to construct with length 6, this will be distance 6 will be optimal.
So that means you're able to collect more errors?
Yeah, so basically that is option. So basically what we are doing, given n and k, I want to construct a code with maximum distance possible, so that you can collect more and more errors. Right?
Like D minus 1 by
D minus 1 by correct.
So how this table got updated?
How this table is updated?
1998.
Yeah, but now so actually there is a Marcus Besson who did some earlier work on this area. I think he did the quantum having an hexacode constructed, and so at that point of time, people in coding theory community used to construct these tables. So he took initiative, he registered a domain code tables.de in Germany, and he's maintaining all these tables. So everybody, so whoever discovers new code, they contact him and he updates it. You will know what is happening right away, right? You can check the table. So obviously there is a lot of gap here. Of course, this is very close gap. इतने साल से पहले इतना आसान तो नहीं होगा, right? But for a larger ones, of course, there is a gap. But who knows that people have brilliant ideas for constructing these quantum codes, right? If you can fill these gaps by some construction, then that is fine. I think FDPRAIT मैथ थोड़ा नहीं करते हैं, इसलिए मैंने सोचा कि you some favor of that, right? Otherwise, pictures हैं.
Any questions? Any further questions?
Any questions?